Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 4 of module 7. In this module we were considering numerical methods for solving ordinary differential equations initial value problem. In the previous lectures we have covered several numerical methods for solving ODE problems. Specifically we started off with Euler's method, the Euler's explicit and implicit method. And in the previous lecture we did the error analysis of for Euler's explicit method, and we found that the Euler's explicit method had a local truncation error of the order of h squared. That means that the error varied with square of the step size that we chose in order to solve the ODE problem using Euler's method. Then we considered Runge-Kutta family of methods, and it is not just a single method but it is a family of methods. And we called it nth order Runge-Kutta method, and the second order Runge-Kutta method had an accuracy of order of h cubed, RK4 had accuracy of the order h to the power 5. We had derived the error analysis for RK2 method, we did not derive it for RK4 method, we only stated the results for the RK4 method. And then we also stated that RK5, the best RK5 that we could get, that also has an error of the order h to the power 5. As a result of this, when we actually go from a fourth order of an RK4 method to an RK5 method, we do not get an improvement in the local truncation error, and that is the reason why the RK4 method is perhaps one of the most popular methods for solving the ODE initial value problems of what we said of non-stiff nature. So that is what we considered, and then we looked at solving a particular problem for a plug flow reactor. And so the physical problem means that there is a tube of a certain length L, and we have the way of certain length L and volume V, and we have species A flowing through that tube, and we said that the flow rate was some value f, and there is a rate of reaction that is taking place. There is a reaction taking place A going to B with rate of reaction equal to K times Ca to the power 1.25. Okay, and we solved this particular problem analytically, algebraically, and we got the solution. And then in the previous lecture of this module we looked at Euler's explicit method and to solve the problem, and the overall problem that we get, problem definition that we get, is dC by dV, where C is concentration of species A at any location in the plug flow reactor, and V is the volume of plug flow reactor starting from this end of the reactor, was equal to minus K by F times C to the power 1.25. And this was the problem that we were trying to solve for value of K equal to 1 and value of F equal to 2. As a result, we obtained the ODE that we had to solve in the form 1 by 2 C to the power 1.25 as the right hand side for this ODE, starting with the concentration C at volume V equal to 0 as 1. So whenever we have ODE, we also require the initial conditions. In this case, since there is a single variable and it is a first order ODE, we require one initial condition, and given this initial condition we solve this problem using the Euler's method. And we solve this problem for 3 different values of h, for h equal to 1, h equal to 0.5 and h equal to 0.25. Okay, So what I will do now is I will go back to Microsoft Excel. We will take off from this particular location and then compare what the results of Euler's method are with results of the RK2 method. Okay, and the RK2 method that we will choose for today is the midpoint method. And for the midpoint method, what we obtained was K1 equal to f of yi comma ti and K2 equal to f of yi plus h K1 by 2 comma ti plus h by 2, and the slope s that we said was just equal to K2, which resulted in yi plus 1 equal to yi plus h times K2, where K2 was nothing but our s. Okay. So this is the midpoint method. We will also use the midpoint method in order to solve this problem, and finally we will use the RK4 method as well. Okay. So most of this lecture will essentially cover solving the same ODE problem first with RK2 method and then with the RK4 method. And in RK4 method we had K1 as same f of yi comma ti, K2 we computed as f of yi plus h K1 by 2 comma ti plus h by 2, K3 we computed at f of yi plus h K2 by 2 comma ti plus h by 2, and K4 was computed at f at yi plus h K3 comma ti plus h. Okay. And then s was just a weighted average 1 by 6 multiplied by K1 plus 2 K2 plus 2 K3 plus K4, and our yi plus 1 was yi plus h times s. Okay. So this all derivations we have done in lecture 3 of this particular module, solving the Euler's method using Excel. We have covered in the previous module. In this particular module we are going to cover the midpoint method, and then we are going to cover the RK4 method. Okay. So let us now go on to Microsoft Excel to try to solve the problem that we are interested in. Okay. So let us now use our Microsoft Excel to solve the problem using the higher order or more accurate methods, and what I have in front of me is just the method that we had used in the previous previous lecture of this module, and we are trying to solve dc by dv equal to minus c to the power 1.25 divided by 2, starting with c0 equal to 1.0, and we had solved it for h equal to 1, for h equal to 0.5 and for h equal to 0.25. Okay. So this is what we had done in the previous lecture of this module, and these were the error values that we obtained. Okay. So this is what we had obtained, and for h equal to 1 this is how the error changes. As we had seen that the error starts with 0 because at volume equal to 0 we exactly know what the starting condition is, and as we move away from that particular volume and as the volume increases we see that the relative error increases. In this particular example it increases monotonically, but there is no reason why this particular error needs to increase monotonically always. The other thing that we also observe is that the error more or less falls linearly. So when we go from h equal to 1 to h equal to half, there is this much big jump in the error, or this much big decrease in the error. When we go from h equal to half to h equal to 1/4, the decrease in the error is half of what the original drop in the error was, and we can look at this when we see the results for volume v equal to 5. There is a 40% error for h equal to 1. For h equal to 0.5 we get the error almost at 19%, and for h equal to 0.5 we get error at 9.5%. So we see that the error is approximately decreasing linearly as we are halving the h value. Now what I will do is I will try to solve this particular problem using the midpoint method. So first what I'll just do is I will just copy this particular worksheet at the end, and I will just rename it as midpoint method. Okay, and I'll just delete all this and we will just go for now midpoint method. Okay, and first we will use this midpoint method we'll use midpoint method with h equal to 1, then we will use midpoint method with h equal to half, and we'll show how the error behavior changes. So I'll just delete all the results that we had obtained, and I'll just move this particular error graph over here. Okay, so what I'm plotting over here, what I have over here is the volume of the reactor, and the volume of the reactor we start off with volume V equal to 0. The initial value for this particular problem is the concentration starts at 1, and so we have the concentration Ci plotted over here. We don't need F anymore, we need K1, we need K2, and we need our slope value S. Okay, those are the things that we are going to require for solving this method using the midpoint method. Keep in mind the midpoint method is a second order RK method, which means we need K1 and K2. For a fourth order RK method we will need K1, K2, K3 and K4. Okay, so our K1 was nothing but F, K1 was F computed at Yi. Okay, I am not writing Ti right now because our expression over here in this particular problem, if we compare this expression with dy by dt, our concentration C is the variable y and our concentration V is the independent variable t. K2 was going to be function f computed at yi plus delta divided by 2, that is the midpoint between Ti and Ti plus 1. So that is yi plus h multiplied by K1 divided by 2. That is where that is the location at which we compute our f for getting our value K2. Okay, so K2 is going to be negative 1 by 2 multiplied by Ci plus h into K1 by 2, right. So this is the overall expression that we ought to get. Now I will replace this Ci with the location of this cell over here. So I will just go over here and click. Okay, so the location of the cell is C6. Our h value is the step size, so I will choose the step size over here, and if you recall, what we used to do earlier was put the dollar signs so that when we drag and drop this in Microsoft Excel, this does not change, and K1 we are going to replace it with this quantity. Okay, so this becomes our f computed at yi plus h times K1 divided by 2. This is yi, that means the value in this particular cell, plus h, this is the value in this cell, multiplied by K1, which is the value in this cell, divided by 2. Okay, and the whole thing has to be raised to power of 1.25. Okay, and that is our expression. Okay, so we will just review that expression. It is half, or rather it is minus half multiplied by Ci plus h times K1 divided by 2, the whole thing to the power 1.25. This is the exponent 1.25 that we have over here. Okay. Now the S value for our midpoint method is equal to 0 multiplied by K1 plus 1 multiplied by K2. So our S value is nothing but K2. Okay. So now we have everything that we need in order to compute our C1. Okay, I will delete these two guys over here, and our Ci plus 1 was nothing but Ci plus 1 is nothing but Ci plus H multiplied by S. And now what I will do is I will replace Ci, H and S with appropriate values. So Ci is this particular value, our H step size is the value in this cell, and our slope is the value in this cell. Okay, and as we have been doing all the time, I will put the dollar signs over here to represent that as we drag and drop this particular quantity, this H should not change. Okay, so I will again drag this down over here, drag my K2 down and drag my S down. The true value that we have, I will just drag this all throughout. Okay, and now what we need to do, as this is what we have been doing throughout the various modules in this particular lecture, we can highlight this entire row and drag it until the value of V reaches 5. Okay, so we will just go ahead and check whether for any arbitrary point whether our equations are correct or not. We will press F2 and this is what we see. Ci plus 1 is Ci plus H multiplied by S are computed at time I. So everything depends on the values that are previously known at time I. Everything at I plus 1 depends on values previously known at time I, and therefore this is an explicit method. We will check our value of K1. K1 should be minus Ci to the power 1.25 divided by 2. So it is minus Ci to the power 1.25 divided by 2. This is exactly what we get, and K2 is again minus half multiplied by Ci plus H by 2 multiplied by K1 whole to the raised to the power 1.25. So it is minus half multiplied by, this is Ci plus H multiplied by K1 divided by 2. This divided by 2 is because we are computing it at the midpoint, and the entire thing raised to the power 1.25. Okay, so everything that we have over here is now we are assured that it is correct, and we can now look at the errors, and the errors are these are the errors that we get. So the error initially of course is 0 because there is no error, the value of initial concentration is known perfectly, and then the overall error starts increasing gradually, and that for volume V equal to 5 we have 10% error in computing the numerical value using the midpoint method. If you recall what we had in Euler's method, we had I believe 40% error, right? Yes, so we had 39.4% error when we use the Euler's method, and when we are using the midpoint method we have 10% error. What I have done is I have also created another worksheet where I have just written down all these errors. These are the errors that I have obtained for the Euler's method, and I have just written them down. This is the error for midpoint method. We have just calculated 10.32%, which I have just put over here. I have also pre-calculated errors of RK4 and error of midpoint method for different H values. We will get to that particular slide in a few minutes. What I am going to do is I am going to show you how easy it is to go from this stage to calculating, doing the calculations for midpoint method for a different H, for H equal to 0.5. So I will just delete all these guys that I had developed before. Okay, so these were the results using midpoint method. We highlight this entire row and we just drag it below until the value of V reaches 5. Okay, so all we had to do was change the value of H over here to 0.5, and we can just check the values of Ci. So Ci is Ci plus 1 is nothing but Ci plus H multiplied by S. K1 should be minus c to the power 1.25 divided by 2, so that is minus c to the power 1.25 divided by 2. Our K2 should be minus half multiplied by c plus h by 2 multiplied by K1, the whole thing to the power 1.25. So, I will click F2 and we will be able to see the formula. Okay. So, c is equal to minus half multiplied by this Ci plus h multiplied by K1 divided by 2, this whole thing raised to the power 1.25. Okay. So, now what we are going to do is just compare the errors of the two methods compare the errors of the midpoint method using h equal to 1 and h equal to 0.5. So, with h equal to 0.5 at volume 5, the error is 2%, the error was about 10% when we started with h equal to 1. So, now that we have solved this problem using the midpoint method, what I am going to do is we will just compare the midpoint method with the previous Euler's method. What we will do is we will just see, we are starting from the same initial volume and the same initial concentration, and we have plotted both how the numerical values of the concentrations are changing as well as the true values of concentrations are changing, and here I have noted down the error between the true and the computed value Ci. These are the relative errors, not the absolute errors, and what I am going to do now is for volume V equal to 5, I will see what the error we are getting from the midpoint method is, and I will copy this error into a different worksheet. Okay, and in this worksheet I have the errors from the Euler's method that I have put over here, and on this place I will just do paste special, and I just want to copy the value, I do not want to copy the formula, and the value of the error using the midpoint method for h equal to 1 was 10.3%. Okay. So, that is what I have put over here. Now, if I want to run this particular problem for a different value of h, for h equal to 0.5, that is also pretty simple. I just need to change this to 0.5, okay, and everything is taken care of over here. I will just take this last line and just drag it down until I reach volume V equal to 5. I can delete rest of this stuff, and the error that I get for h equal to 0.5 is excuse me, the error that I get for h equal to 0.5 is 2% error. Again, this 2% error I will just copy it and paste it in the new worksheet, okay, that I have called as comparison. So, this is comparison between errors from various methods, okay, and then again I want to calculate this value at 0.25. I just changed the value of h. Since the value of h is changed to 0.25, the final value of the volume is 2.5 because we have just computed it 10 times. So, I will just drag it 10 more times for 10 more rows, and I should be able to get volume V equal to 5. Okay. And so, now the error has decreased from 2% to about 0.4%, 0.45% to be more precise, and I will paste this error again over here. So, the error in midpoint method has gone down from 10% to 2%, from 2% to 0.5% approximately. So, it is almost, the error is decreasing by almost 1/5, and again the error has decreased by almost 1/4 or 1/5 when we go for when we half the h value, okay. And what I will do is I will half the h value further and go to 0.125, and for 0.125 again this I will have to drag it for 20 more columns, and when I drag it for 20 more columns and 20 more rows, sorry, I will delete these guys, and now the error is 0.1%. So, error is approximately decreasing by 1/4 when the step size is decreasing by 1/2. So, it looks like what happens is the error is decreasing by 1/2 to the power 2 every time I am halving the step size. So, on this log, so what I have done over here is For the Euler's method, I have plotted h, the step size in the x axis, sorry, and the error using Euler's method on the y axis, and I have made them both log plot, and on the log plot the error h versus error becomes a straight line for Euler's method. Actually the slope of this straight line is going to be equal to 1 for the Euler's method. What I will do is I will also plot the midpoint method. So the way to plot an additional data set of data on this plot is right click and choose select data, add the data, the series name is going to be midpoint method, the x values are going to be the step sizes, and the y values, the original y values, I will just delete them and then again click on this and I will choose the values in the midpoint column, okay, and it is done. So now what we have is this particular line represents the Euler's method and this particular line represents the midpoint method, okay. So what we see is that the errors in Euler's method are greater than the errors in midpoint method. The slope of the Euler's method is lower than the slope of the midpoint method. The slope of Euler's method is actually slope equal to 1. It does not seem like 1 from this particular graph simply because the step size goes from 0.1 to 1, whereas the error goes from 0.001 to 1, and that is the reason why it does not look as if this slope is 1 and this slope is 2, but actually the slope of this line is approximately 1, the slope of this line is approximately 2, okay. So this was the results using Euler's method and using the midpoint method. What I will do next is we will try to use the Runge-Kutta method in order to solve this problem. So in order to use Runge-Kutta method, what I will do is I will just copy this midpoint method to a new sheet. I have what I have done, I will just show you again. What I have done is right clicked on this tab, click on move and copy, I click on create a copy, that means this particular midpoint method worksheet is going to be copied, and I will choose to copy before the worksheet called comparison, okay. And now this midpoint method has now been copied as midpoint method 2. I will rename this as RK4 method, okay. And again for RK4 we are trying to use the same type of scheme to compute DC by to compute C at various time given dC by dV equal to minus C to the power 1.25 by 2 and C0 is 1.0, and we want to compute with h equal to 1. I will just go down over here and excuse me and delete all these guys, okay. This error column I will and the slope columns, these two columns I will move it 2 positions to the right, 1 and 2, and the reason for that is I want to accommodate K3 and K4, okay. And so that everything is visible to you, I will just select this and change the font size to 18 so that everything is clear, okay. So now for RK method our K1 remains the same, K1 is just going to be f of yi, okay. So K1 there is no problem, K2 is going to be f of yi plus h multiplied by K1 divided by 2, okay. This is our K2. Keep in mind that in this particular example the function f is just a function of y, it is not a function of t, that is why I am using a shorthand notation. If it was also a function of t, then instead this would have been f of yi comma ti, okay. So I am just not writing this ti to simplify the notations at this point of time because our function f is just a function of yi. Now our K3 that we had is function f of yi plus h multiplied by K2 divided by 2, okay. This is our K3 and K4 was nothing but f of yi plus h multiplied by K3. This was our K4. Okay, remember geometrically what we said this means is K1 means slope computed at the initial point yi, K2 means the slope computed at midpoint yi plus half, K3 means slope computed at midpoint again yi plus half, but in this case y is computed using K2 instead of computing using K1, and finally K4 is the slope computed at the end point yi plus 1. Okay, so sorry, rather ti plus 1, and these are the various projected slopes that we compute, and our s, the actual slope, is going to be 1/6 multiplied by K1 plus 2K2 plus K3 plus K4. So I will write that down over here as well. S equal to 1/6 multiplied by K1 plus 2 multiplied by K2 plus 2 multiplied by K3 plus K4. Okay. So this is our S. Okay. Now that we have all these, we are now ready to do all the computations. I will delete all these guys from here. The true values I do not need to delete because true values remain the same. Okay. So K1 is the same as we had in the RK2 method. K1 is always going to be f of yi. So f of yi is negative of c to the power 1.25 divided by 2. Okay. So we have this, this is not a problem. K2 is now going to be again the same as previous, because in midpoint method also we are going to use the formula computed at the midpoint. So again K2 we do not have to change, but what I will do is just for our own sake, we will just copy down, or we will rewrite or rewrite this formula for K2. Okay, I will increase the font size to 18. Okay. Okay. So now K2 is going to be equal to f of yi plus h multiplied by K1 by 2. So let me just write what h multiplied by K1 by 2 is. I will write that in brackets. So this is h multiplied by K1 is this guy divided by 2. Okay. So that is the value of our argument of this function. So yi plus h multiplied by K1 by 2. So yi is this guy plus h multiplied by K1 by 2. Okay. So in the brackets the term that we have is the argument of the function f. Okay. C6 is yi, B3 is our h. When we are going to drag and drop, we do not want our h to keep changing. So I am going to put dollar signs in front of this. Okay. And then our D6 is our K1. So our argument is C1 plus h multiplied by K1 divided by 2. Okay. It is just the h multiplied by K1 which gets divided by 2. Okay. Now this is our argument that has to be substituted over here. So what we have is negative 1 by 2 multiplied by the argument to the power 1.25. Okay. So I will write that down over here, minus 1 divided by 2 multiplied by the argument raised to the power 1.25. Okay. And this is our K2. So just for comparison, that is the same K2 that we had obtained earlier. Okay. So now we have K1, now we have K2 as well. K3 has a similar formula. So I am just going to drag K2 and drop it to the right hand side. However, there is a problem over here. So we will just do F2 and see what that problem is. Now for K3 we have minus half, okay, multiplied by the argument to the power 1.25. So minus half multiplied by this particular argument to the power 1.25. That argument is yi, which is this particular guy. So it is actually yi plus h multiplied by K2 divided by 2. Okay. So now our formula is correct. It is minus half multiplied by yi plus h multiplied by K2 divided by 2 plus h multiplied by K2 divided by 2, this whole thing to the power 1.25. Okay. I will press enter and we will get the value of K3. So K4 is going to be equal to negative half minus half multiplied by the argument is y1 or sorry yi, which is this guy, plus h multiplied by k3, that is the argument. Ci plus h k3 is the argument. For h we need to put dollar signs, so that when we drag and drop that thing does not change. Now this is our argument, the argument has to be raised to the power 1.25 to the power 1.25. So it is minus half multiplied by yi plus h k3 to the power 1.25, that is our k4. Okay. And our s is going to be 1 by 6 multiplied by k1 plus 2 multiplied by k2 plus 2 multiplied by k3 plus k4, that is going to be our s. Okay. So we now have k1, k2, k3, k4. Now let us look at computed at time I. Now let us look at Ci plus 1. Ci plus 1, I will just write that down, Ci plus 1 Ci plus 1 is nothing but C of I plus H multiplied by S. Okay. So C of I plus 1 that we have over here is, I will just rewrite this, C of I plus 1 over here is equal to C of I plus H multiplied by S. Okay. And for H we will again put the dollar signs over here. Okay. And that is our concentration computed at volume equal to 1. Okay. Then what we will do is we will take this and we will just drag it to the next row, and now we have concentrations and K1, K2, K3, K4 and S computed on the next row, and we can just copy all of these and just drag them over here and we have the results. Okay. So now what we see is, and we need to change it from midpoint method of course to Runge-Kutta fourth order method. Format cells, alignment, merge cells, horizontal alignment will be center. Okay. Fourth order Runge-Kutta method. Okay. So now we have the results for RK4 method using H equal to 1, and for H equal to 1 the error is 0.08%, which is much lower than the errors that we had obtained earlier. I will copy this and paste it in our comparison section, paste special, and we just want the values. Okay. Now what I will do is I will just change the format of the numbers. Rather than a general format, I will change it to the scientific format with 2 decimal places. So we get 8 into 10 to the power minus 4, that is the error that we get with H equal to 1. Okay. Now I do not need all these, so I will just go ahead and delete them, and now we want, what we want to do, I will just save the file right now. Yes. Now what we want to do is recompute this for H equal to 0.5, and we want to see how the error decreases for H equal to 0.5. So with that, now V has gone from H equal to V equal to 0 to V equal to 2.5 when H is halved. So I will have to just select this last row and just drag it until we reach 5. Okay. So now when we halved the overall H, what happened is the error decreased from 0.08% to 0.004%, which is approximately I would say 18 times or 20 times a reduction, right. So if we take the divide this by this guy, we have it essentially the error has decreased almost by a factor of 18. So the error with H equal to 0.5 is approximately 1/18 of the error with with H equal to 1. Now we repeat this with H equal to 0.25. Again we will take the last row and just copy it downwards, okay, and check the error at volume equal to 5, and at volume V equal to 5 the error is 2.44 into 10 to the power minus 6. I will do this, copy this, and I will paste it over here, again paste special and value, and again if we take the ratio of the two, would lie somewhere around 15 to 20, that range. Yes, it does lie in that range, it is 17. Actually what we had seen in the earlier class is error for the local truncation error for the Runge-Kutta method is h to the power 5, that was the local truncation error. This one shows the global truncation error, and the global truncation error is of the order of h to the power 4, which means every time we are going to half the h, we are going to increase the accuracy by approximately 16 fold. Okay, that is what we saw earlier, the accuracy was increased by approximately 18, factor of 18, now the accuracy has increased approximately by a factor of 17 and a half. Okay. Let us now again repeat this RK method for h equal to 0.125. Okay, I will just chosen this particular row and just copied it below, and this is the result that we get. Okay. So, now the error has decreased to 1.5 e minus 7. Okay, I will do paste special, I will just place the values, and again I will try to take the ratio this divided by this, and this ratio is now 16.7. So, in all cases the ratio is indeed hovering around 16, that is when we take the ratio of the accuracy of RK4 method using h and using h by 2. Okay. So, just to recap, what we get is when we halved the h in Euler's method, the accuracy the error also halved, or the accuracy doubled. When we halved the h in midpoint method, the accuracy changed by a factor of 4, and when we halved the RK method, the h in the RK method, the accuracy changed by a factor of 16. Okay. These are all what are known as global truncation errors. Okay. Now I will add another plot over here, okay, where the name of the plot is going to be RK4, the x axis values are going to be the h values, and the y axis values. You have to delete the value 1 over here before you choose the row. So, here we have chosen this row, sorry, not the row, the column, and we have the result also over here. Okay. As you can see, RK4 method is significantly more accurate than the Euler's method. The Euler's method using h equal to 0.125 has an accuracy of about 4%, whereas RK4 method using h equal to 1 has an accuracy of 0.08. Keep in mind that RK4 method uses 4 computations of the slope. So, the slope is computed at yi at the midpoint twice and at the end point, whereas Euler's method is just going to use the slope computed only once. So, f for each implementation of Euler's method, the function f of y comma t is used once, whereas for each implementation of RK method y of t is used 4 times. So, a fair comparison would be when Euler's method is used with h equal to 0.125 versus RK4 method used for h equal to 1, and even that comparison shows a significant accuracy of the RK4 method over the Euler's method. Okay. And this is the plot of the log plot of how error changes with the step size. Okay. And this particular line is going to have a slope of -4, this line has a slope of a slope of 4, this line has a slope of 2, and this line has a slope of 1, even though it might not look this way because of the range of this ordinate versus the range of the abscissa that we have over here. Okay. So, that is essentially what we have with respect to comparison for the various RK methods with the Euler's method. What I will do is I will just recap what we have done so far in the 4 lectures in the previous 3 lectures in this particular module. The overview, we are going to consider Runge-Kutta family of methods, we have considered Euler's method, we have talked about implicit and explicit method, we have considered higher order Runge-Kutta method, we have done error analysis. What is left to do is the stability analysis that will be done in the next lecture in this module. Okay. Now let us give an overview of RK2 methods. We are going to use RK2 method as a weighted average of slope computed at 2 points between Ti and Ti plus 1, where K1 is the slope computed at Ti and K2 is a slope computed somewhere between Ti and Ti plus 1. Okay. We use Taylor series expansion to get the derivation for RK4 method, and these were the results that we got. Sum of the weights W1 plus W2 should be equal to 1, W2 multiplied by P2 should be equal to half, and W2 multiplied by Q21 should be equal to half again. In yesterday's in the previous lecture of this module, we had used the term W2 multiplied by P and W2 multiplied by Q. Instead of that, I have used the subscript 2 and subscript 2 comma 1 in below P and Q, and the reason for this will be evident from when we go to extension to higher order RK methods. Okay. And the standard way of writing these weights is in a tabular format of this type. We draw 2 lines, one vertical line and one horizontal line. To the left of the vertical line, we will write P2, P3, P4 and so on for up to Pn for RKn method, and to below this horizontal line we will write the weights W1, W2 and so on up to Wn, and the Q values come over here. Okay. So for example, let us consider the midpoint method. In midpoint method, the value of P2 was equal to, the value of P2 that we chose was half, because value of P2 we chose was half, the value of Q2 was also half. Okay. And the weights that we got were 1 for W2 and for W1 it was 0, and this is represented as half half for the P and Q values and 0 and 1 for the weight values. There is no Q2 term or Q22 term in a second order RK method. The Q22 term would be Yi plus Q21 multiplied by Hk1 plus Q22 multiplied by Hk2. But keep in mind, if we had Q22 multiplied by Hk2, we will not have an explicit method anymore, because K2 itself will depend on K2. Okay. So this will become a semi implicit method if we were to have this term as non-zero. Okay. And then in Yoon's method, for Yoon's method what we said was P we said was equal to 1. When P was equal to 1, Q also we got equal to 1. So P and Q are both equal to 1. Based on this, our W2 was equal to half and W1 was also equal to half. So what we have is P and Q were both 1 and 1, and W1 and W2 are both half and half, and there is no Q22 term. Okay. And that is essentially the Yoon's method. And finally we also talked about the Ralston's method, and for Ralston's method our P2 was equal to 3/4, Q21 was 3/4, and the weights were 1/3 and 2/3. Okay. That is about the RK2 method. We can then go on to discuss about a general RKn method, and a general RKn method will be written as a weighted sum of slopes K1, K2, K3 up to Kn. So it is H multiplied by W1 K1 plus W2 K2 and so on up to Wn Kn. K1 is of course as before computed as f of yi comma Ti, and Km is a slope computed at some points within that particular rectangle that we had shown in the geometric interpretation. So it is computed at Ti plus some quantity Pm multiplied by H, and Yi is H multiplied by again a weighted sum of K1, K2, K3 up to Km minus 1. Okay. That is how the RKn method will look like. Okay. And for RK4 method we will have K1 and then this expression for K2, K2 will consider Q21 and P2, K3 will consider to Q31, Q32 and P3, and K4 will have Q41, Q42, Q43 and P4. Okay. So, the particular table in case of RK4 method will have P2, P3, P4, Q21, Q31, Q41, Q32, Q42, Q43 and the weights W1, W2, W3, W4. Okay. So, as long as this table is given to you and I tell you that this is going to be the RK4 method, you can then use these particular values in order to solve the ODE using RK4 method. Okay. So, that is where we will end this lecture of module 7. In the next lecture we will start off again considering the RK4 method. We will again look at the geometric interpretation of RK4 once for one final time before proceeding on to the predictor corrector methods. Okay. Thanks.